Hey everyone, welcome back to my channel, and today we're going to build a complete machine learning project using Python and scikit-learn. We'll be classifying iris flowers using logistic regression, and I'll walk you through every step of the process. By the end of this video, you'll understand how to load and prepare data for machine learning, scale features for better model performance, train a logistic regression model, evaluate your model's accuracy. Let's dive right in. First, let's make sure we have all the necessary libraries installed. You'll need scikit-learn, which you can install using. Now, let's start by importing all the modules we'll need for this project. Let me explain what each of these imports does. Train test split splits our data into training and testing sets. Logistic regression, our main classification algorithm. Accuracy score and classification report for evaluating our model. Standard scaler to normalize our features. Load iris loads the famous iris dataset. Now let's load our dataset. The iris dataset is a classic machine learning dataset with 150 samples of iris flowers. Each sample has 4 features: sepal length, sepal width, petal length, and petal width. We're trying to classify flowers into 3 species: setosa, versicolor, and virginica. Notice I'm using descriptive variable names here, features instead of just X, and target instead of Y. This makes our code much more readable. Next, we need to scale our features. Why do we scale? Well, our features might have different ranges. For example, sepal length might be measured in centimeters, while another feature might be in millimeters. Scaling ensures all features contribute equally to our model. The standard scaler transforms our data so each feature has a mean of 0 and a standard deviation of 1. This is also called z-score normalization. Now, let's split our data into training and testing sets. I'm using 80% of the data for training and 20% for testing. The random state equals 42 ensures our results are reproducible. You'll get the same split every time. The stratify equals target parameter is really important here. It ensures that our training and testing sets have the same proportion of each class. This is crucial for getting reliable evaluation metrics. Time to train our logistic regression model. Logistic regression is a great algorithm for classification problems. Despite its name, it's used for classification, not regression. It works by finding the best linear boundary to separate our classes. I'm setting max iter equals 1000 to ensure the algorithm has enough iterations to converge, and random state equals 42 for reproducibility. Now, let's make predictions on our test set. Our model will now predict the species for each flower in our test set, based on the patterns it learned from the training data. Finally, let's evaluate how well our model performs. The accuracy score tells us what percentage of predictions were correct. But the classification report is even more valuable. It shows precision, recall, and F1 score for each class. Precision: of all the flowers we predicted as setosa, how many actually were setosa? Recall: of all the actual setosa flowers, how many did we correctly identify? F1 score: the harmonic mean of precision and recall. And there we have it. When I run this code, I typically get an accuracy of around 97 to 100% on the iris dataset. This dataset is relatively easy to classify because the 3 species have quite distinct characteristics. Let me summarize the key points from today's tutorial. 1. Always scale your features when using algorithms like logistic regression. 2. Use stratified splitting to maintain class balance. 3. Set random states for reproducible results. 4. Use descriptive variable names for cleaner, more maintainable code. 5. Evaluate with multiple metrics, not just accuracy.